Hello, everyone. My name is Simon, and it's such a great pleasure for me to present my final project here about the quantifying the economic value of urban greenery with geospatial double machine learning. So the big idea here is to test whether the urban greenery in city centers is actually linked to stronger nighttime light economic activity and whether the relationship works partly through urban coolings. So I used the remote sensing data across multiple different hot climate cities, and then I estimate the effects using double machine learning, plus a spatial extension with the graph neural networks. So to give you a bit of the background, and I'm also a candidate of the ALM project in data science at Harvard Extension School. And apart from that, I'm also a PhD candidate student at the University of Cambridge in the urban planning and data science. So my background is really in the urban design and urban planning. And urban greenery is really a very broad concept. It can include parks, street trees, and green roofs, and many other any green elements within the city. So in the urban planning and design, the greenery really matters because it changes how people view the experiences of the public spaces, and it can also make the public spaces much more comfortable, more attractive, and just more usable for our daily lives. But even though greenery is really widely discussed in the academia, especially, but there are still some gaps. So, firstly, there are not that many quantitative and micro-scale studies that connect the greenery to local economic realities. And secondly, the mechanism is not always quite clear. So, does the urban greenery help the economy mainly because it looks nice for its aesthetics value, people get attracted, or is because it's especially in the hot cities, it helps cool down the areas, and then people will feel much more comfortable in the colder areas, especially in the summers or the hot cities. So the project like to ask that in the urban core, and does more greenery lead to stronger nighttime lights, and how much of that effect is actually via the direct versus mediated by the land surface temperature. So this slide is a quick roadmap. I firstly built a multi-city polygon by year dataset from the remote sensing. But before I jump into the details, I'd like to outline my methodology. So the double machine learning is a causal inference framework that uses machine learning to flexibly model high-dimensional confounders, and while estimating the treatment effects with orthogonalization and cross-fitting to reduce the bias. And I'm gonna introduce much more variables later, and I can actually estimate the total direct and indirect effects using double machine learning. And finally, I will extend the nuisance learning step with the graph neural networks, which can capture the spatial dependencies. So here's the main statistical setup. The nighttime lights are the outcomes, the why we are interested, and NDVI, which is the normalized difference of vegetation index, is a treatment. The land surface temperature will be the mediator, and there are going to be another set of the indices, and which please allow me to introduce here, and the NDWI, and it's actually the water index, and the BI is the building index, and the MI is the moisture index. We have the population densities here and the cities and year fixed effects. So we control for these variables, and in this case, double machine learning really helps because it separates the causal parameter we care about from the complicated prediction tasks. And this part is handled by the machine learning models. And then I can actually estimate the total effect without controlling for the land surface temperature. And I can estimate the direct effect while controlling for the LST, which is land surface temperature, and compute the indirect effect in the form of total effects minus the direct effect. And for the data collections, I focus on 12 cities, which are generally from the hot areas because the cooling mechanisms should be much more meaningful there. And also I do not use the full administrative boundaries of the cities, and instead I keep only the dense built-up cores. And this is because the signals in the nighttime lights and temperature can reflect the real city center environment. And the NDVI, the vegetation index, comes from the Landsat 8, which is a satellite launched by NASA. The nighttime lights come from the VIIRS Black Marble product, which is also from NASA. The land surface temperature and all the other set of the indices is also computed from the Landsat 8 data, which is from NASA. So, and then these are all the raster data, and they are all zonally aggregated to the same urban core polygons. And regards to polygons, in very soon you're going to see what I really mean by polygons, and where I can include all the different control variables, including the population density, and it's a raster we can aggregate on both all the polygons as well. And this is actually supplied by the word pop has the official population data until 2020, but then after that, we only have a WordPop community estimations version, but this is still really valuable. And regards to selecting the urban boundaries, this slide shows that what I mean by urban core selection. The goal is to actually avoid including the large suburban or the rural areas, and that can obstruct the nighttime light signal and add too much noises. So the polygons are trimmed to actually represent the most built up and central part of the city, and this is the spatial unit we're going to use across all the variables. And in the bottom, you'll see two pictures where I crop the most urban, dense, and built-up areas, and by using the central of cities, the bottom left is Singapore and the bottom right is Doha. So this is the two examples from the 12 cities I'm using, and now we can actually start our analysis, and I'm going to start the demos, but before we actually start, and in the step 2.0 in my notebook, it provides that's how we can actually read the data and also the details on the reproducibilities. I set the seed for the overall environment, and also I set the seeds for the TensorFlows and the PyTorch to make sure that the results are reproducible. And if you want to run my notebooks, and you need to download my data, and then you need to upload the data onto your Google Drive and use the Colab to access it. Or alternatively, if you think there's too much effort, you can also just download my data. I also have the alternative strategies which allow you to just directly upload my data into the Google Colab for analysis. And so if we start from the step 2.1 to 2.3 in my notebook, it's about the apart from the environment configuration, installing some very necessary libraries, and it also reads the exile, clean some of the null values because it sometimes happens to be zeros, and as the satellite did not really capture any data, and merge all the relevant data together, because when I crawl the data and from the satellites, they have been stored in the separate sheets. And then we can do the log transformations, which is very important because there are going to be some linearity problems, and log transformations can scale the very noise and potentially capture the growth rate as well. And then the city and year fixed effects have also been added as well as Boolean values. So they're going to create 11 columns for the cities and another 11 columns for the years. And this is where the deep learning really comes in step 2.4, 2.5. And there's going to be like a problem here. It's actually, I used for the double machine learning, I used a package called double ML. But this package actually expects the scikit-learn style learners. So I have to encapsulate my Keras MLP architecture into a scikit compatible regressor. So that means that it needs to have fit and to predict functions, and the output must also be in NumPy arrays format. So it sort of like imitates exactly what the predict and the fit functions do if you use the scikit. So we encapsulate that into Keras ML regressor, and then we can use a pipeline to actually, with standard scaling, and because neural networks are sensitive to the feature scales, and then I can plug that learner into the double ML packages to estimate the total effect and the direct effect, and that should work. And after I get the total and direct effect, and we can just compute the indirect effect using total effects minus the direct effect. So for this output, they are computed using the double ML libraries. And we can also estimate the p-values. We get the p-values directly for the total and direct effect, but for the indirect effect, and the very ideal situation would be that if we can do the bootstrappings just to repeat this for different times and will be more confident about the uncertainties we're going to have. But in this case, the bootstrapping will cost too much time, and I do not suggest to run my bootstrapping code in my notebook because that is going to take forever. But alternatively, you can also run a normal approximation to approximate and estimate the p-values, and there's an assumption associated, which is that the total effect and direct effect may not be related, so the covariance is going to be 0. But still, we get all statistically significant p-values for the total direct and the indirect effects, and the coefficients are actually all positive. So this suggests that the urban greeneries can indeed attract some of the nighttime lights and contribute to the local economy, but it's just based in the urban core and city dense center. But I'm really motivated to do the second part, which is the graph neural network based double machine learning, because the graph neural network is advantaged because it take account of the spatial dependencies, which we'll be able to see later. So for step 3.1 to 3.4, and it's fairly similar with before. And starting from step 3.5, I want to talk about the shapefiles importations, just for those of you who want to reproduce my analysis. So you need to download my ctshapefiles.zip, and from the canvas, you need to upload it on the Google Drive, or alternatively, you can just also upload it. And because I do have the code set up for you, and then I define a function to load and read the geometries of the shapefiles. And because these are spatial data, that contains the geometries and the coordinates and informations. And then based on the coordinates, I can calculate the spatial adjacencies, and they're actually going to be very important for us to compute the edges, and because they are the distances between the urban cores, the nodes. And in this price, an example about the graph we are going to actually produce. So the step 3.6 and 3.7 from my notebook, and actually merge the panel data and create the polygon data and construct the graph. So firstly, we map each of the panel city to its matching shapefile city names, and because they used to be two separate files, and we need to keep the nodes, and the nodes values will be the polygon values. So for an example, it can be the values of the NDVI vegetation indexes, can be the value of the nighttime lights, and later on we're going to do the analysis on that, and then we do the log transformations, adding the fixed effects, the year end places fixed effects again. We can also produce the node indexes for each polygon for each year. And because this is panel data, and finally, we are also going to build the spatial temporal edges. And for the bottom two are the examples for one city, Bangkok, in 2013, I believe. And these are the two different ways to illustrate and the networks you're going to get after we construct the overall graph. And we're going to have this graph for all the 12 cities across the 12 years, and they all contain the nodes, informations, and the edges for the future analysis. And so in step 3.8 to 3.9, I actually execute the double machine learning based on the graph neural networks. But again, we need to encapsulate the PyTorch. And in this time, I followed the lectures from week 14 and used the graph convolutional networks architecture. And then I encapsulate this GCN into a scikit-learn compatible estimator using class double ML GCN. And then in the double machine learning, I can use the double ML package again and just directly call on this class. But when I execute the graph neural network-based double machine learnings, some very interesting results do come out. And firstly, if we observe, the total effect and the direct effect are still very statistically significant, and the coefficients are also positive. And in terms of the scale, it's relatively similar to the one we get from the MLP double machine learnings. So it can also stand as a robustness check to actually make sure that even if we are taking account of the spatial adjacencies, we're still getting some very sensible results saying that the urban greeneries can still attract the nighttime lights. It's not just simply because of the pure spatial perspective. perspectives. But if we look at the indirect effect, and in this case, it's much more reliable because we actually conducted the bootstrapping instead of the estimations, because the PyTorch is probably much more powerful. It's quicker for us to conduct the bootstrapping, and even though still going to take some time, but I do include them here, and we can see that it's not statistically significant anymore. So this may actually indicate that if you take account of the spatial dimensions and perspectives, and it may just absorb the mediating effects, and we know that spatially the urban greeneries is very spatially correlated with the lowering of the temperature. But once that spatial relationship has been accounted, it doesn't really seem like that the temperatures can attract a very huge amount of the nighttime light activities, and especially through the channel effect from the urban greeneries. And so this actually gives us very valuable insights into the urban planning, which is to focus more on the aesthetics of the urban greeneries, and rather than just like blindly building so much of the different patches for the urban greeneries and just to lower the temperature. And so this is my analysis and project. I hope you enjoy that. Thank you very much.